When Heisenberg and Bohr proposed the Copenhagen interpretation of quantum mechanics in the 1920s, many physicists at the time objected to a model that included indeterminism. In other words, it was thought that there should be a complete theory that could account for all observable behavior. In particular, it was Albert Einstein who refuted the probabilistic nature of quantum mechanics, famously declaring, "God does not play dice." Einstein, Podolsky and Rosen all argued that there must be some hidden variables in a system that, if known, could predict the outcome in the way that classical mechanics can. To explain this, imagine flipping a coin. Before flipping and observing the coin, quantum mechanics would describe it as being in a superposition of both head and tails. When flipped, quantum mechanics says the outcome would be purely based on chance, and we cannot determine what this might be until observing it. However, if we had known the initial force, angle and height at which the coin had been flipped, classical mechanics would be able to perfectly predict how it would land. Einstein believed equivalent variables existed in quantum systems that, if known, would remove any indeterminism involved. Any so-called collapse of the wave function is really a collapse of our ignorance of the hidden variables. To make this case for hidden variables, Einstein used the notion of quantum entanglement. But what is entanglement? If a system with no overall spin splits into two particles, say two electrons, by conservation laws, we know that the overall spin of the system must be zero. Hence, one electron must be in a spin-up state and one in a spin-down state. However, if the particles are separated before any observations to a distance, such that they would have to move faster than the speed of light to communicate, the laws of relativity seem to break down when one is observed right after the other having opposite spin. This is resolved with hidden variables, which would determine from the moment of separation the spin states of both particles. Recent experiments have measured entangled particles within less than 1/100th of a percent of the travel time of light between them.